Hello again, my name's Jenny Lynch. Welcome to our Castro in the Classroom session for this afternoon. Joining us today, we're very excited to have Professor Tamara Davis, who's a world-renowned astrophysicist from the University of Queensland, and I'm sure you're going to enjoy her presentation this afternoon. So I'll hand over to you, Tamara.
Cool, thanks very much, Jenny. It is fantastic to be here. Welcome everybody. I'm glad that you could come and join us. As Jenny said, I'm an astrophysicist. I get to travel around the world using big telescopes in Chile and Hawaii and space, although I haven't actually gotten to visit those ones yet. But talking to people who are inspired by what they do and about astronomy, space, and all the things about how the universe works. So I'm going to tell you a bit about the excitement that I have with this kind of topic at the moment. Ooh, and it looks like we might be welcoming another school. Hello there, hopefully people who are just attaching. Ooh, I don't know if it worked. Anyway, I'll keep going. So here in Australia we've got something called the Centre of Excellence in All-Sky Astrophysics, and we're a group of 7 universities, or people at 7 universities, more than 150 people, all trying to figure out stuff about the universe. One of the themes of that centre is the dark side of the universe, and that's what I study. I'm actually leader of the dark theme, and we try and figure out what the universe is made of, because we've discovered that a lot of the universe out there is stuff that we can't see. We see it by its effects, like the gravitational effects, but we can't see it directly. And so in that way, it's a bit like looking at, trying to study the wind by watching how the leaves of trees move. You know, you can't see the wind, but you can see its effects on the branches of the trees moving around. And so that's the kind of thing that we're trying to figure out, the wind, by looking at how the trees move. We're trying to understand the dark side of the universe by looking at how things like galaxies move. So hands up, I can sort of see you there. Hands up if you know what this picture is of on the screen. I see a couple of hands. This is actually Halleys Comet. I saw this when I was about 10 years old, and I was amazed at the time because I remember thinking, you know, it's pretty and all that, but the thing that amazed me most was that humans understood gravity well enough to know that Halleys Comet was going to come back in like just over 75 years. I thought that was, how on earth do we know that gravity works that way and orbits work that way and that kind of thing? And I was inspired by that, and it's led me to learn a lot more about how that all works. So, okay, hands up if anyone can identify this object. Does anyone know what this is? Yell out to your teacher if you know what this is. I can't hear you, but see if you have any guesses. I'm not sure if anyone got it right, but the answer is this is the Large Hadron Collider, and it's a 27-kilometre around ring around which we accelerate particles to close to the speed of light, bash them together, and from the shrapnel try and figure out what the nuts and bolts are that make up matter in our universe. I was lucky enough to get to visit there just a little while ago. This is me with a whole bunch of wires and stuff in the background, all the nuts and bolts of how the experiment works. And here's me. I was really nerdly excited to get to go and see this machine. It was sort of cool. Big tunnels underground, and got to wear cool hard hats and that kind of thing. Now, next question. Does anyone know what this is? This one's a bit harder. This is the SuperKamiokande neutrino experiment. These guys down here, they're in a boat. This is all water, and this is like deep in a mine, and these are all photodetectors. Like, they detect flashes of light, and what happens is they fill this whole thing up with water, and occasionally this like elusive particle called a neutrino will go through, and occasionally it will hit something. It interacts so weakly that if you just wait 1 second, whoosh, 1 billion neutrinos just passed through you, and you didn't notice. Or did you notice? Anyone? You probably didn't notice because they interact so weakly. That's why you need these vast caverns underground to be able to detect them. And what these guys in the boat are doing right now is they're trying to repair these things because one of them burst and it sent a shockwave around that sort of burst every bulb in the place, which was unfortunate, but it's fixed and working again now. Okay, now this one is a cool experiment as well. This one's called the Hubble Space Telescope, and hopefully some of you might recognise that one. But this is really cool, and the reason I've shown you these is that the Hubble Space Telescope and the kind of research we do is trying to answer many of the same questions that are being answered by things like the Large Hadron Collider and the neutrino detector. We're really trying to figure out the laws of physics and how they work. And the different, we go to try and look in space to answer these questions rather than only doing experiments here on Earth, because space is an amazing natural laboratory. Like, we have even though the Large Hadron Collider is a 27-kilometre around ring, arguably the biggest experiment that humankind has ever constructed, still it's only a 27-kilometre around ring on just, a little-ish planet, actually, around a normal star that's only one of 300 billion or so stars in our galaxy, all of which have nuclear furnaces going on inside. And a galaxy that has a supermassive black hole in the middle of it that's billions of times the mass of our sun. And that's just one of hundreds of billions of galaxies in the observable universe. So the universe naturally puts on experiments on time scales and length scales and energy scales that we just can't hope to possibly replicate here on Earth. So that's why we're doing what we're doing and looking up in space. Now, by the way, I think if they have questions, they can type them in and things. Yeah, there'll be questions at the end, so think of questions if you have any. I'm happy to answer lots of questions. Now, this image here is the Hubble Ultra Deep Field. Now, what you're seeing is a picture of empty space. It might not look like empty space, but what was done here is that the director of Hubble took the Hubble Space Telescope, pointed it at a patch of sky where we couldn't see anything else. Like, it was a blank piece of sky. There's no stars, no galaxies or anything like that. But left the shutter open for 11 days. So it's like you take a really long exposure, and over 11 days light slowly accumulates until you're able to see really faint things that were just too faint to discern before. And this is what you get. What you're seeing here is just a whole heap of galaxies. Basically, every dot in here is another galaxy like our Milky Way. Even the really, really tiny ones, they're just really, really far away. There's a couple of stars in there, but it's pretty much all galaxies. So it's just a beautiful array of the things that are out there in the universe. Now, the next thing I'm going to show is a zoom out from another Hubble Space Telescope image. And the purpose here is to try and give you a visceral sense of just how far modern telescopes can see. Because it's that kind of the new technology that we have that's allowed us to learn so much about the universe. So here we are, we start with an image from the Hubble Space Telescope, and as we zoom out, it gets superimposed on images from other telescopes, all in the correct part of the sky, but just telescopes that had a sort of a wider field of view and less zoomed in. And as you zoom out, you zoom out, you zoom out, eventually you get to some sort of constellation you might recognise. So this just hopefully gives you a visceral sense of just how far we can see. And the story I'm going to tell you now is about discovery, about the discovery of the expansion of the universe, and the discovery of our ability to measure how that expansion has been changing, which has only just become possible in about the last 20 years. So let's go and have a look at this. There's a couple of images here. There's the guy with the telescope there on the left that's Hubble. So he's the one that the space telescope got named after. And he's doing two things that we never do on a modern telescope. One, he's smoking, and two, he's actually looking through it. Of course, these days we have digital cameras, so we sit in our nice, comfortable control rooms and we see the images appear on the screen. Now, the plot that I'm showing there is some of Hubble's data. Now, the thing he's famous for is discovering the expansion of the universe. And that was discovered by doing two measurements. The first was actually made possible by an astronomer called Henrietta Swan-Leavitt, who figured out that a certain type of star that varies with time, called a Cepheid variable, always you can figure out by how fast it changes how bright it is, which means you can measure its distance. It's called having a standard candle, and it's exactly the same as if if I was to hold a candle up and run really close to you and hold it close to your face and then run 100 metres down the road. Even if you couldn't see anything else, you could make a pretty good guess at how far away I was, just because you know how bright candles tend to be. So that's the concept of a standard candle. By looking at how bright something is, we can tell how far it's away. The second piece of information came from the Doppler shift. So this is from the velocity of galaxies. Now, if you're familiar with the rainbow of light that you get when you take normal light and put it through a prism, then when you have the Doppler shift, the wavelengths of light get shifted either to the red if something's moving away from you, or to the blue if it's moving towards you. It's sort of the same effect that you get if you hear a racing car come, and it comes and goes meow as it goes towards and away from you, and the meow part, the high-pitched part, is the sound waves all getting compressed as they're coming towards you, and then the wrong part is them being more spaced apart as they're going away, and that's what's happening with, you get the red part of the light. And what Hubble discovered, thanks to Vesto Slipher and Milton Humason, who did some of the observations of the spectra, was that all of the galaxies were going, they're all moving away from us, and the further they are away, the faster they're moving. That was the discovery of the expansion of the universe, and the fact that there was probably a Big Bang. Because if the faster things are moving, or the furthest things are moving away faster, then when you reverse that, you find that everything was all compressed into a very small volume, or to a point, if you take that all the way back to the beginning of time. So that's the idea. The galaxies are all moving away from each other, and we have Hubble's law, which just says that the velocity of their motion is proportional to their distance. Now, Hubble published that paper in 1929, and ever since that, we've been trying to figure out whether the expansion is going fast enough to escape, so the galaxies will all escape from each other and expand forever, or whether galaxies are going to slow down and the universe will recollapse. So it's very much like if I take a pen and I throw the pen up in the air, it comes back down. Gravity is pulling it, it comes back down. But if I throw this fast enough, the escape velocity of the Earth is about 11 kilometers per second. So if I throw this at 11 kilometers per second, which is very fast, then if there wasn't a ceiling and if there wasn't any air resistance, this would escape off into space and never come back. So the question was, do the galaxies have the escape velocity? Are they moving fast enough to escape their own mutual gravitational attraction? Or will gravitational attraction win, slow them down, stop them, and make them fall back together? We didn't know, because although it's relatively easy to measure the expansion, measuring how that expansion changes is hard. And so that's what, in the 1990s, a discovery that supernovae, exploding stars, could also be used as standard candles. That's what that helped out. So supernovae are exploding stars. They tend to get bright and fade over the course of maybe a couple of months. And you see an example of that here. We think that what's happening is a couple of stars merge together, and one of the types of stars, a little one, will explode. And that's sort of shown here. But these supernovae are really useful because they all explode to approximately the same brightness. And that brightness is incredibly bright. One single exploding star can outshine all of the light from the other hundreds of billions of stars in a typical galaxy. So there's an example here where this one supernova is as bright as that's one star, is on the outskirts of the galaxy, is as bright as the entire galaxy. So that means as long as we can see galaxies, we can see these supernovae. That makes them better than what Hubble used, because the Cepheid variables, those stars, you can only see relatively close. So now we can see much further away, and we can compare what happened back then, because further away is also back back in time, the light has taken billions of years to get to us. So we're looking at the universe as it was billions of years ago. So when we look at the universe as it was billions of years ago and look at how fast it was moving then compared to now, we can compare the two and see whether the universe is slowing down enough to recollapse. Now, that was done, that's just another example, that was done in the 1990s by these two guys and their teams. There was in total 52 people in the two teams, but on the left you've got Brian Schmidt from the High Redshift Supernova team, on the right you've got Saul Perlmutter from the Supernova Cosmology Project, and they're pretending to fight at a conference here because their teams were sharing the same telescope and competing at time, and there was a bit of a race going on to figure out who could measure this first. Now, I joined the teams to test supernovae in about 2004, which was just when I finished my PhD. So when I did my undergrad in physics and did a degree in physics and astrophysics, and then went on and did a PhD in astrophysics, which is a time where you just purely do research. And after that, I got recruited by both of these guys actually to try and help build a space telescope to measure the acceleration of the expansion of the universe better. So I'll show you some pictures of the things that we used. When I was designing the space telescope, I was also helping out with the observations of the projects in progress here on the ground. Here's one of the telescopes we use. It's called the Cerro telescope. It's a 4-meter mirror, so a very big mirror, up in the mountains in Chile. Now, I was doing this in 2004, 2005-ish, and we were, the way that you discover supernovae is you observe the same patch of sky night after night, and you see if anything changes. So here's an example of one half of one of our images, and if you zoom in on something about that big, you get something that looks like this. This is the before and after image. Now, can anyone tell me where the supernova is in the after image? I want you to have a little bit of a look, and in each of your classes, tell your teacher if you can see where the supernova is in the after image. I'm going to give you 30 seconds to do that, so have a chat for 30 seconds. Okay, I think I see a bunch of arms pointing, which is a good sign. Now let's see if any of you got it right. This is I call this slide "Why This Is Hard," and it's the reason that we needed really, really good digital cameras on advanced telescopes to be able to see this. Because what we do is we digitally subtract one image from the other, and when we do that, we see this. The difference between the images is quite small. It's a bit noisy. But you see two dots here and here. One of them, these are the two things that changed in that image. One is not a supernova, the other is. So you probably can't see it, but it's the bottom of this fuzzy blob up here. There's a tiny little dot, which is the supernova. So there's a supernova happening on the edge of that galaxy. So you can see why, if we were just looking at photographs and you didn't have computers to help you out, it would be really, really hard to actually see these for real. This one, I think, is an active galaxy, which is just a galaxy whose black hole in the middle is sucking in stuff, and it changes a little bit with time. Now, despite the fact that it's really hard, we've become very good at it. Here, I did some work in 2007-8ish with this team called the Sloan Digital Sky Survey. Here's an example of 500 supernovae or so that we had from that, where here's some nice examples where you've got the galaxy here and the blue dot beside it is the dot that's the exploding star, the supernova. Now, once we've gone there, you also go to the bigger telescopes, the really, really big ones. These are 8 and 10 meter class mirrors to get spectra, so you get the spectrum of light, the rainbow of light from the supernova. And here I am at the VLT, which we're very imaginative when we name telescopes in astronomy, so that's the Very Large Telescope. This is the mirror of the VLT, That's me taking a selfie. So you can see relatively how big these telescopes are. They're really enormous pieces of kit. It's pretty cool. And here's this is where you live. You live underneath this dome when you're working at the VLT. And that's the VLT on top of the mountain. And here's some people filming James Bond Quantum of Solace at the telescope. That's them blowing up the astronomer's residence. That dome is on the top here somewhere. And when I stayed there, that was my room. Of course, that's all computer-generated graphics. So luckily they didn't really blow it up. Anyway, the end of this story is when we were finally able to measure the change of the expansion of the universe, we discovered a surprising thing. And this was before I joined the teams, but the discovery was that the universe is speeding up. Something is causing the expansion of the universe to accelerate. And that goes against anything that we thought we knew about how gravity worked. We always used to think that, what goes up must come down. But what we discovered is as strange as if you took this pen, I threw it gently in the air and watched it accelerate off into space. For some reason, gravity is pushing instead of pulling. And we don't yet know why, but the cause of that acceleration of the expansion, we give the name dark energy. And that's what they won the Nobel Prize in 2011 for. So here you see Brian Schmidt and Saul Perlmutter, the two who were pretend fighting before. They're looking a little bit more respectable now and receiving their Nobel Prizes. So anyway, I've been talking about dark energy. This is what causes the expansion of the universe to speed up. For a long time, we've also known about dark matter, which clumps and it holds galaxies together. We've known about that since the 1930s, so it's really well established. But there's these two things. This dark matter is not made of atoms, it's made of something else, and it holds galaxies together, and it does a whole bunch of other things. Dark energy accelerates the universe. What we're trying to do is get new observations to try and figure out what these two things actually are, because if we're going to understand them from a physics point of view, we really want to figure out what they are. So a couple of interesting things. Here is that Hubble Space Telescope image that I showed before, and I said that we just exposed our telescope for a really long time, like opened the shutter and just let more and more light in, and we saw more and more galaxies that were too faint to see before that. Well, it used to be that, exposed for longer and you see more galaxies, but with this image, it's pretty much no longer true, because we're looking so far back in time with this image that we're looking back to a time before galaxies even existed. So the most distant galaxies that we're looking at here are at least 12.5 billion years old, and our universe is only 13.8 billion years old. So we're looking back almost to the first billion years of our universe. And just to put that in perspective, you're looking at light here that was emitted before the Earth even formed. The Earth is only 4.5 billion years old. So when we look at this sort of light with our telescope, we're looking at light that has been travelling since before our sun even existed. It's really astonishing to think about. But if you if you go past this and you look in microwaves, you're able to see this, which is the cosmic microwave background. And this is one of the most concrete proofs we have that the Big Bang really did happen. This is the leftover afterglow of the Big Bang, basically from when the whole universe, everywhere you looked, was as hot as the surface of the sun. So if you'd lived back then, it would have been like living in the interior of a star, but a star that went everywhere in all directions. The whole universe was as hot and dense as the inside of a star. So if you look at it, if you imagine yourself in the inside of this sphere, you can look out and all of those hot and cold spots that you're seeing as red and blue are tiny little fluctuations in that microwave background, and they ended up forming all of the galaxies and structure that we see today. So if you start from those initial conditions, I'm going to skip these pictures, but when you chuck them into a supercomputer and you see how the universe evolves from there, you get something like this. And this is a numerical simulation done in a supercomputer of galaxies forming. And so you start with those fluctuations we see in that leftover radiation from the Big Bang. By radiation I just mean light, leftover light from the Big Bang. And here you see all of this beautiful structure of galaxies forming. Something like our Milky Way would just be one of these fuzzy blobs on the outskirts. This big white thing in the centre is a cluster of galaxies, many thousands of galaxies all forming into one big blob. It's pretty cool. So you get these big empty spaces, you get filaments of stuff and galaxies. And when I returned to Australia after I'd done my supernova work, I joined a team called Wiggles, and we mapped the distribution of galaxies in the universe, and we detected the imprint of those patterns that you saw in the leftover stuff from the Big Bang in the distribution of galaxies. And this is sort of what you're seeing here. We weren't able to map anywhere near the entire sky. We just looked at these yellow regions, which are just sort of a few different directions in the sky. And every dot that you see there is another galaxy. And the ones on the outskirts emitted the light that we're now seeing about 8 billion years ago. So we mapped this distribution of galaxies and saw the imprint of sound waves that happened when the universe used to be so dense that sound could still travel. Okay, well I better wrap it up so we have some time to have questions. I'll just note a couple of very, very quick things. One, why do we care so much about doing all of these physics experiments and tests? And well, I did also get to give a talk recently on warp drives, because this stuff that's causing the expansion of the universe to speed up could actually maybe be something that, could end up helping create warp drives. We certainly try and look into figuring out whether we can make things like hoverboards, whether if something's causing the expansion to speed up, something has some sort of anti-gravity property somewhere. Either our laws of gravity need revision, or we can maybe have some stuff there that we can use as an anti-gravity thing. So we'll see if we can figure that out. So that's sort of one of the reasons that we do this kind of thing. And the final thing is, I mentioned that the universe is, we're trying to understand all of this stuff, dark energy and dark matter, that we can't directly see. And so when have we ever been asked to believe in so much stuff that we can't see before? And I would argue that the example I gave at the beginning, the air, is an example of that. Because if you think back just 200 years ago, we didn't know about the periodic table. We didn't even know that matter was made of particles. All that has come really very recently. So if we didn't know what the air was a couple of hundred years ago, then look at how far we've come with our chemistry, etc. now. Let's see it might take another couple of hundred years to figure out what dark energy and dark matter are, but who knows what we'll be able to do once we get there. So thanks very much, and I'll take any.
Thank you very much, Tamara, and I really enjoyed that presentation. I hope you all did too. I think we'd like to see just who managed to find that supernova before. Did anyone spot it? Hands up. Did anyone spot where the supernova was? No, it's pretty difficult. I think you proved your point. Now we do have about 10 minutes. If anyone has any questions they'd like to ask Tamara, teachers, if you could unmute your microphone when you're ready to ask a question, that'd be great. Or teachers, feel free to ask questions too.
Yes. How many other women do you see in your field? Like, are there a lot, or are you one of the few?
Okay, so was that from Taramara, is that right?
Yeah.
So yeah. The question was about how many women you see in the field.
Yeah, traditionally there's been a lot more men than women in the field. So, and when I became professor at University of Queensland this year, I was only the second ever female physics professor there in the 100-year history. So that's showing you that the girls are a little bit underrepresented. So girls out there, quick, we need more of you as well. But certainly at PhD level and things like that, at the moment, there's a lot of girls. It's, I think, at least 40% women. So the statistics for the up-and-coming aspiring astrophysicists are pretty good. But it's not uncommon for me to be in a situation where I'm the only girl in the room. And occasionally I give talks and there's not that many other females in the audience, like more like 5% or something like that. Especially the more mathematical that they get. But that's changing, and there's been a big push lately to avoid. There's sort of a lot of stereotypes that are being broken lately, and so it's being a bit more equitable.
Any other questions?
There you go.
I've got a question. When you point a telescope in the night sky and you have it on long exposure, isn't the position of the night sky changing?
Yeah, well, even when we have relatively short exposures, so a short exposure for us would be 5 minutes, say, you have to have the telescope tracking. So there's a little motor in the back of the telescope that makes the telescope track with the stars. And in detail, I glossed over a bit when saying that it was an 11-day exposure. What you actually do is you take many slightly shorter exposures, so like say an hour and a half, and then you add up all the light from all of those many different exposures. So you don't risk stuffing up a single 11-day exposure. You know, if you stuff up one exposure of the hundreds that you take over 11 days, it's not so bad. So you actually end up stacking a lot of individual images to get to the total of 11 days.
Great. And are there any other questions? I can see another one from Tamara.
Was physics something you were interested from a young age, like during high school, or was this something you got interested in later?
Well, I never was one of these people who had some grand ambition of what I wanted to do when I grew up. I really didn't know. I knew that I had, some aptitude for science, and I sort of liked maths, and I loved my science fiction books and that kind of thing, and my fantasy books. But when I went to university, the choice that I made for course, I chose physics amongst the sciences partially because it had the most options, and it had the most flexibility in it. And then I sort of just, my philosophy is always never plan too far ahead, because who knows what the future holds, but always make sure that whatever you're doing right now is fascinating. Because then if you do something that's really interesting now and you continue to choose whatever is most interesting to you, you end up being qualified for something that you love. So that was my philosophy that's worked well for me.
Okay, another question?
So Monash, looks like they have one.
Are you aware of any stars in the solar system that are likely to become old and turn into a black hole soon, and what would happen to the solar system?
Well, not in our solar system, because our sun is the only star in our solar system, and that's going to blow up in about 5 billion years, so we've got a little bit of breathing space. Indeed, before our sun blows up, we're probably going to collide with Andromeda, another galaxy, which could also be entertaining. But we have looked at stars nearby. So the closest star is about 4 light years away, and it's not going to blow up anytime soon. And we're not in any imminent danger from the local area, as far as we can tell. But if one did go off nearby, like if a supernova went off close enough, it could be really damaging. It's like you get a burst of high energy radiation, and it could sterilize the Earth. It's one of those things that's on the list of possible global catastrophes that would be very bad. But luckily, the statistics show that one of those will only go off close enough to us, maybe a couple of times in the lifetime of the sun. And there are speculations that some of the mass extinctions in the past were spawned by something like that happening.
So you mentioned that we're going to collide with Andromeda, but if that's the case, you said that we were, like the galaxies and everything were expanding, so wouldn't we be moving apart instead of like attaching?
Fantastic question. So while all of the galaxies in general are moving apart from each other, if you're close enough, so our galaxy also had to form from something. Really local stuff can be caught by the local gravity. And so it's our small local group, so us and Andromeda and several dozen galaxies around us are all part of our local group, and we're gravitationally bound. And it's that sort of scale of thing compared to the next group of galaxies and the next group of galaxies that are all moving apart from each other. So you can have little local differences where, like, locally, clearly this pen's going to fall. It's not going to accelerate away. And that's, so locally Andromeda is just doing this. But if you go out beyond Andromeda, then it's the rest of the galaxies that are moving away. And actually, if you look at Hubble's initial diagram, the Andromeda is on there, and it's a dot that's moving towards us. It's sort of, there's scatter about that relationship, where you see that it's not just a perfect moving away with distance. There's some randomness to it, and that's some of the local motion.
I think we've got time for just 2 more questions.
So what about Dennison or Janali, who I don't think have spoken?
Does Janali have a question there? Yes? Just remember to unmute your microphone first.
Hi, I was wondering if you had seen the movie Interstellar, and if so, was there any merit to its science?
Yeah, Interstellar was a really interesting one because they tried hard to get the science right, and some of the black hole visualizations in particular, they published a couple of papers on that, and how the light is warped around the black hole, and the time dilation around the black hole, how you would age less if you were near the surface compared to if you were out in space, and that kind of thing. Spoiler alert, sorry. But all of those things were all very valid, and it dives into rampant speculation at the end, but if you're trying to visualize extra dimensions and stuff, you sort of have to do that. But the one thing that I would note from Interstellar, that whenever anyone asks me about it, is that it demonstrates beautifully that no matter how good our technology becomes, even using things like wormholes and stuff to travel through space faster than light, it is really, really hard to get to other planets, especially other planets in other solar systems, and they're almost guaranteed to be more crap than Earth when we get there. So let's look after this planet.
Okay, just one more question. Do we see any hands up? Dennison? Question from Dennison College? Yes?
You have to unmute.
I was just wondering, what's your favourite part about the job you do?
Favourite part? I love the fact that I get to go to work each day and figure out whatever problem I think is most interesting and work on that. Like, the freedom of the job is amazing. One of the other things I love about the job is that you get to travel all the way around the world, like go to exotic locations in Chile and things like that for telescopes, but also just to work with collaborators. So I spend a lot of my year traveling. I work with a bunch of people in Europe and in the States and people in South Africa and things. And so I spend a lot of time going and traveling and working with some of the most amazing people that I know. So really, really, inspired, intelligent people who are doing stuff that they're passionate about, and that's amazing. I mean, I've got this, just like last month I got to go, so I've already, as I should have showed, I guess I've worked with and published with 4 different Nobel Prize winners. Last month I got to go to, I went to a meeting in Madrid, then I went to another one in the Netherlands, where I got to be on a panel with yet another Nobel Prize winner and debate, the nature of space and time with this other Nobel Prize winner in front of an audience. And then I got to fly to Switzerland, where I got to go to visit the Large Hadron Collider, and the BBC took me up on a glacier somewhere in the mountains, and we filmed a documentary about warp drives and anti-gravity. And then the other thing you get to do is you get to supervise students and get research students and come up with new projects and interact with people and also teach. So there's an enormous variety in the job. So basically there's a heap to like about it.
So lots of favourites.
Lots of favourites. Sorry I didn't pick one. But,
Well, now if you do have more questions, please feel free to ask your teacher to email them to us. And we've also given your teachers a Twitter handle, Twitter hashtag, if you want to send any questions that way as well. And teachers, I'll get in touch with you with a feedback form, and we'll also be releasing our schedule for 2016 very soon. But to finish with, would you please all help me with thanking Tamara for that wonderful talk. Thank you very much, Tamara.
Thanks all.
Thanks a lot for joining us today.
Thanks, everyone.